Okay, here's part 8 of my LinuxCNC HAL tutorial series. In this one, we're going to take a look at what goes into making a real-time HAL component. And we're going to focus on the thcud module that we used in the last video and make some tweaks to that for how we're going to use it in the next video. This topic does get a little bit more programmery, but don't skip it just, in case you aren't a programmer, all right? Firstly, it's still good to review anyway, just for general knowledge's sake and for learning how LinuxCNC works. Secondly, if you want to set up a THC like we're going to do in the next video, you need to have these changes, otherwise it isn't going to work. And lastly, the stuff we're going to cover here, it's really not that bad. Okay, if you've done any Arduino programming, this stuff is really pretty similar. And I'll walk you through it and draw the parallels between it so you can see just how that works. And by the end of this video, you should at least be able to write a very, very simple component of your own. So if you remember back in video 5 on ohmic probing, at the end of that one, I went through some absolutely convoluted, horribly stupid HAL just to do some comparison things at the very end. And it was, several lines of it didn't make really any sense at all. But you'll see, after going through how a component works on the inside here, that we could replace all that messy HAL with like a single line in a component file. And between the video here and the docs and the PDF, under the menu I've shown a million times before, and then the other examples included with LinuxCNC, you should have a pretty easy time following along. Anyway, in that video, we took a look at all the HAL components available to us, and we found them by using a couple of Linux tools. So we already know that we have a component called and2, right? We use that one all the time. So you can use the locate tool on Linux to look for files named like and2. So we do that, get a short little list, and there are a few duds in here, like command to, hand to, expand to, right? Things that we're not looking for. But this one here looks pretty promising, and that's over in user real-time modules LinuxCNC. Like it has the real-time modules for LinuxCNC, right? And here we've got a whole bunch of these KO files, including one for and2 and every other component we have available in our HAL. Now, what is a KO file? It's basically the compiled and installed version of one of these components. Kind of similar to a DLL in Windows. It's a binary file full of ones and zeros, nothing you can really read. The computer can read it and can run it, but it's not the source code that we're really interested in. The important part about this directory is that it gives you the view of what you've actually got installed and available at your fingertips. And that's important because, as I mentioned in that other video, not all of these are listed in the big old PDF doc, right? A couple of them are missed in there, so if you want to see everything you can use, look in here and then double check the man pages for things related to all of this. But if these are not the source files themselves, well then where do they come from, right? Well, you might have noticed in that locate list, there's a file up here for and2.comp, and those comp files are what make the majority of your HAL components. A few of them are special and written by hand from scratch, but most of them come from starting with a comp file and then building that into the .ko. And that takes care of a lot of the boilerplate of writing your own HAL components. Now, I have this here on my system because I keep a full git checkout of the LinuxCNC source code. So basically, if you head over to github.com LinuxCNC/LinuxCNC, you can get yourself a copy of the code by copying the download link, going to your home directory, and doing a git clone of the URL, and just specifying a directory to save it into. Now, I've already got a copy of it saved, so not going to download that into, ADSLK, whatever gibberish is specified there, because I've already got it saved in git-linuxcnc. But it's that easy to get, and once you've done that, you have the full history of the LinuxCNC code right here, on your computer. So you can do like a git log and take a look at all the commits that have been happening. And in fact, the latest commits are ones that relate to Plasma C, the feature replacement for thcud. That's still kind of in the works. But yeah, go figure, right? Anyway, so yeah, now you get a copy of this, and we can look for where we've got that component exactly. Let's see, and2.comp, and that's in source HAL components. There we go, and view and 2. Now, it is also important to mention that because we just went and grabbed the latest code from GitHub for Linux CNC, the stuff we're seeing here might be slightly different from what you're running on your system, right? I've got Linux 2.7 installed, and I think the code here is currently for like a pre-release of version 2.9. So it's a little bit further ahead, but as far as a reference copy goes, it's still pretty good. And if you want to, you can always go back in the history and check out the exact version of the code that you are personally running on your machine. Because that's the power of, open source code and Git. Anyway, this component looks messy, but let me walk you through it. At the top here, we have a few definition lines, right? You're specifying components, pins, whatever, their names, optionally some documentation, and then every line ends in a semicolon. So we got component and two input and gate, semicolon, right? Pretty straightforward. Then we've got definitions for the in0 pin and the in1 pin we've been using, right? They're both pins, inputs, and they're bits, right? They're true and false values, just like we've seen before. And they don't have any extra documentation because they're pretty straightforward. Then we've got the output pin, right? Also a bit, a Boolean value, and it's called out, right? That's the output we've seen before as well. But then what's all this mess right here, all this extra garbage? Well, that is the documentation on this pin, right? Because the semicolon to end the line is actually several lines down right here. And this triple quoted thing, this is a block string. So this all is that one bit of documentation for this pin. And if you read it, you'll notice this is really the content from the man page, right? Just some extra markup. It's, out is computed from the value of in0 and in1. And it's just marking out, font bold, font regular, font bold, font regular, and then some spacing stuff. So if I actually open up another man page for that, man and 2, you'll see that's the exact text right there, right? As it appears right over here. So in fact, we're just going to remove that for a moment, just to kind of clear the space, make it a bit easier to focus on the stuff that's really important. Because documentation is important, don't get me wrong, but it's not the meat of the thing right here. Then we've got a line that defines the function. So we have that and2.0 function we add to the servo thread or the base thread as we're building out our HAL. So we say function, and this underscore is the shorthand for calling it and2.0, and2.1, and2.2 as we include more and more of them. No FP is the syntax for saying that it doesn't have any floating point calculations in it. I've talked about that before with the base thread and servo thread, that your base thread is the fast one, where your step gen, and pulse generator and all that stuff runs, but it can't do floating point computations. Whereas the servo thread is a bit slower and can do floating point computations. This one's specified as no floating point, so it can work in either of them. And in case you're not familiar with the lingo, floating point just means decimal. That's a number with decimal in it. Turns out that math is harder for computers as well as humans, right? So it slows them down and it just can't run at base thread speeds. And we've got license specified. This line here is a double semicolon acting as a delimiter between the top and the bottom, with all this stuff here really just being basic boilerplate, and the stuff down here being the real part of the component. So if you've ever done any Arduino programming, it's pretty similar to the loop function, right? In Arduino you have begin, and it does your initialization, and you got loop. And loop gets called over and over and over again as the Arduino runs, in a loop. Here, the function method gets called just over and over again every time your servo thread or your base thread executes. So 1,000 times a second or 100,000 times a second is just running over and over, once again, in a loop. So you can see how these parallels kind of form, right? I guess the one thing that's different is rather than doing like a digital write or an analog read or any of those methods, we're simply assigning values to these pins, right? Because in Arduino speak, you are writing pins on that physical chip, either high or low, 5 volts or 0 volts. Whereas here, you are assigning values to HAL pins, right? So it's strictly in software. And these HAL pins then can feed signals, they can feed other HAL pins and other components, and maybe it'll eventually go to a physical pin on your parallel port breakout board or something. But as far as this HAL component is concerned, it's all staying in software. And the power port component that gets things to be in reality, that's a whole different story. We're not going to get into that. That's more complicated. But as far as simple arithmetic goes, this is pretty straightforward. And then again in Arduino, you've got begin, it does your setup and defines what your pins are. Typically you do the pin mode, right, in your begin function. Here we have this boilerplate up top, and you're setting basically your pin mode, right? Pin in, and it's a bit, right? It's the same thing. So for arithmetic like this, I guess Probably the weirdest part is you have like a double ampersand, and that's part of C syntax. So if you do any read any tutorials on basic Arduino programming or basic C programming, the same general thing. It'll tell you this is the way you check to see if either this if both this and this are true. So for that ohmic sensing HAL I did before, that big old mess, that one would have been written something like, let's see, I guess out equals in 0 equals 5. And because, again, in C, double equals is used to test equality between two things, and then a single equals is for that assignment. So we're saying, is this pin equal to 5? If yes, return true. And then we'd also need to change the type of this from a bit to an int. We wouldn't need this one anymore. You change the name, a few other things, but like, really, it's like one line of code to do that messy bit of HAL. And if you got any other arithmetic you want to do or anything more complicated, you just kind of build it up, and overall it's not that bad. Again, especially with all the examples I got in here, you can build some pretty advanced things. And if you want to learn more about all the boilerplate syntax and the stuff that goes along with that, there's details on that in section, I think, 14.13 in the manual. And then again, all the other component files in this directory. So anyway, we're going to quit out of here and not save any of these changes. And now I'm going to talk about how you compile these files, right? So we just have it as a comp file right now. And if we do the HAL compile tool on thcud.comp, and we look, we can see now it's spat out a C file, right? Talk about C programming. It basically takes that comp file and it processes it to give us a file that's straight written in C. Let's take a look at this one, and now we can see what all that boilerplate expands to and how we get all this extra noise. At the very end, we get the actual function, right? So thank goodness that HAL compile lets us write a comp file and save doing all that extra mess. So that's how you process it into a C file, but we're really more interested about how do you install it, and that's done with again HAL compile --install, and you just say thcud.comp, and that will both turn it into the C file, then compile it into the KO file, and then install it for you in user real-time modules Linux blah 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 blah, right? And because you're writing that somewhere where you have system files, you'd also have to add a sudo on that so it has administrative privileges to write to that directory. Now, when you do that, it's going to overwrite the file that's already there. And also, I typoed. Install has 2 L's. There we go. So when you do this, it's going to overwrite the other thcud.ko. And I didn't make any changes, and I didn't save those changes I made, so that'd be fine. But remember, the files we're looking at here are technically for a newer version of LinuxCNC. So if you go installing things willy-nilly in that directory, you might end up breaking something. It's always possible to go back in the Git history and find the right comp file and then rebuild that and reinstall it. But I'd recommend just saving a backup copy of the old KO file if you are going to make any changes, just in case, just make it easy on yourself, save a backup copy. If you bunch it up, you can always put that one back and undo the changes that you've done, right? Anyway, thcud is also in the same directory, so let's get onto that one now. And it's pretty much the same deal here, right? Component thcud, it's a torch height control, up-down input thing. It's got some documentation on the pins you hook up. Let's see. It's got the author license. It has this other option here. This is a new one. So having option singleton, that is why when you do a load RT for thcud, you only have the single instance, or you don't have that thcud.0.1.2 thing. You can only have a single one because this option singleton is set, right? After that, you've got some pins, some more pins, got some parameters. Now, parameters, as we discussed, are not as useful as pins because you can't write to them in PyVCP. So we're going to fix that in the changes we make. We've also got, let's see, one of the output pins here is for the cur offset. That was another bug I mentioned where it wasn't ever putting out the offset, just putting out 0 instead. And in fact, if we look at where else this cur offset gets used, we see it doesn't get used anywhere. They only define it here, and they never assign a value to it, and that's why it only ever read out 0. So you see there's this variable here for offset, but it never gets, that value assigned to this pin, and then you don't get anything, right? So we'll make sure we fix that too. And then we get down to the part that really is the main body of the function. This is where things get, again, kind of programmery, but I'm going to do my best to translate all this, code speak into plain old English so, again, you can follow along. So we're going to start off saying, if we've enabled thcud by writing that pin to true, we're going to do, all the processing for the offset. And first thing we do is see what the minimum allowable velocity is for applying our offsets. Because we have that requested velocity, the current velocity, and the velocity tolerance settings. That in the past video, we just set them all to be 1, just so that we ignore it and let's do manual torch height control. In the future, we're going to actually use the appropriate pins so it will disable torch height control as we slow down to go around corners and things. Right, so this is where we've had that velocity tolerance. I mentioned that's a percentage value, right? So if you say 30, that's really 30% of the requested velocity. So that's 30, times 0.01 times your requested velocity minus your requested velocity means the minimum velocity would be 70% of your requested, right? And it calculates that requested then based on what your feed rate is on your G1 moves. So again, it will scale where it locks at the THC around corners, depending on how fast you're trying to move, as opposed to just using a set speed value. Then we say if we're moving, and we're moving faster than the minimum value, we set our velocity status to OK. Otherwise, we say not OK, and we basically end up skipping all that offset stuff. So now we've got, if the torch is on, and the arc is OK, and we're going fast enough, we allow ourselves to apply corrections. So we read the pins for torch down and torch up. Again, we don't have digital reads in here. We're just using the values straight because this isn't Arduino, it's HAL. But same idea, right? These pins, you just use the values and it's like reading them. And we say if we have the torch down pit set, then we decrement the offset by correction velocity. And that decrement thing, it's the minus equals. Same as saying offset equals offset minus correction velocity. Again, this is just C shorthand. And if we have the torch up pin set, we do offset increment by correction velocity. And that last video I mentioned the correction velocity really isn't a velocity per se, as much as it is the amount you adjust the offset. And you see that's where that comes into play, right? You're not really telling it what speed to adjust at. You're telling it how far to adjust the offset. And then the speed part of it comes into play when the the servo thread runs at a consistent rate. In my case, it runs 1,000 times a second, so you can do the math. If you adjust by correction velocity 1,000 times a second, that is however many inches per minute. And then we write our last C in to be 0, and we'll get back to that in a little bit. Now, when the torch turns off, that's when you try to remove the offsets we've applied. So let's see. We start off with our current Z position and our last Z position, and then take the difference of the two. If that difference is positive, that means we're moving up. So when the torch is moving up and we have a non-zero offset, right? We've applied some offset with the torch height controller, we want to use that upwards motion to remove the offset we've applied. So it sets this removing offset pin, which is really just a debugging pin you can use in your HAL. And it's got two cases here. One for when the offset's positive, and one is for when the offset's negative. So in both cases, we're trying to move the torch up by doing like say a G1, Z1, right? And that would be a motion upwards. So if your offset is positive, it ends up removing that difference from the offset. So rather than moving the torch upwards at all, it simply docks that difference against the offset. So if you've already applied a ½ inch of upwards offset, say your plate was really out of skew. I mean, I guess like an 1/8 of an inch is more realistic, right? Say you moved up by 1/8 of an inch, and you say move it up an additional inch. The first 1/8 inch of that will come away from the offset, and then it will lift up by 7/8 of an inch. And by that point, your offset is gotten set down to 0. And then this whole loop then gets ignored on the next run of the servo thread. Then if you have the case instead where your offset's negative, say your plate was sloped downwards and your torch head controller dropped the torch by 1/8 of an inch. When you say to lift it up by an inch with a G1, Z1, then it will use that to increment against the offset. So the torch will begin moving immediately, but in the first 1/8 of an inch of motion, it will wipe out whatever offset you have set. And that's kind of how it removes that offset between every cut of the torch. Is this even really necessary? Yeah, maybe I would have done this differently. But it does work for the most part. Again, there's a bug that we'll get to in a sec. But that is the idea of what they're trying to do, right? They're trying to count your first intentional Z upward move against any offsets the torch head controller might have applied. But they're not doing that with Z downward moves because, again, with a torch, the upward move is always the safe move, where a torch, a downward move, might run your torch into the plate. So they use that upward move to try to correct that offset before you get to your next cut. Then a bit further down, when we don't have any offset left to remove, we set this removing offset value to 0, again, to help us debug, and we save our last ZN to be our current ZN, where we are right now. That way, the next time this component runs, when the servo thread comes through again, it will have this value now saved as the last ZN, so it can check to see if we are still moving up or not. Then, if we are still applying that offset, we adjust our Z position out, by the in position plus the offset. And in the case where we don't have thcud enabled at all, we simply pass the values through directly as they are. Now the problem I was having was that when the torch turned off, sometimes it would immediately begin to lift upwards. Very, very strange. You can see here, it's not supposed to move until you do an intentional move up. But sometimes it would just do it on its own. I'm not gonna lie, it took me a little while to figure this one out. And what finally made it click for me was that down here, we're assigning the last ZN to be where we currently are. So next time we come through in the loop, this has our last Z position, right? And that way you can tell if we're still moving up. But sometimes, right, when you turn the torch off, it would register it as moving upwards, right? It's because right here, we're setting last ZN to be 0. Just irrespective of where we really are, we're setting last ZN always to be 0. That way, if your current ZN is positive when the torch goes off, it will register that as an upward move, even without you, issuing a G1, Z1, or a G0, Z1, or something to actually move the torch up. It will see that falsely as an upward move. So what you gotta do then is fix this so it's also saving accurately the current position in from this run. So on the next run, it's saving the last position in. The really weird thing was the problem was intermittent. So why? Right? Why the hell would I not even get the problem consistently? Well, that happens because the Z position in pin gets fed off of the, say, the axis motor-pos.cmd, right? The commanded motor position on your axis component. That value keeps track of how far the motor has moved since the machine started. Okay, it's not based on coordinate axis or anything. It's based on where the machine started up. So usually my torch is parked at XYZ all 0. And that's when the torch is also all the way up. That means in typical operation, the axis motor position command for axis.2, the z-axis, is always acting as a negative value. Even if I adjust my G92 coordinates, set like the torch is calling the workpiece z equals 0, that motor position pin is always reading a negative value because it started off at the very top. But sometimes I'm a lazy ass and I don't park the machine before I set it off. And in that case, you can have a positive motor position command value. And then when the torch shuts off, duh, because this has been already written to 0, this Z is a positive value, right? This motor position value is positive, and then it immediately registers a upward move that didn't even happen. So Oh, yeah. Don't you wish you were a programmer, right? Then you could spend 40 hours a week banging your head against the wall, solving problems just like this. Yeah. So what's the fix? Well, if you go to my GitHub project over here, you will not find the exact thcud.comp file that you need with the changes. But underneath LinuxCNC, MISC, and thcud fixes, you will find the instructions as to where to get those files. Now, why the step of indirection there? Well, basically, licensing in software is a whole other clusterfuck. Okay, it's a god-awful mess. And my opinions on the matter tend to align pretty well with this guy's right here. It's a blog by a pretty well-known software author. I'll put a link to it down below if you care to read about the minutia. But suffice it to say that licenses are for lawyers, and lawyers can go fuck themselves. Right? Okay, so that's basically it. And instead of putting that stuff in here, because the thcud.comp file is under the GPL license, which is a very promiscuous license, basically makes everything it touches under GPL. So rather than doing that, I put it under a separate GitHub gist and just give you a link, to where to go to find that here. So if you go to gist.github.com/swolbro, you'll find the one for thcud there. And all a gist is, it's basically a special kind of Git repository hosted by GitHub. That's really like a Git project for a single file. So you can still get this thing here and actually Git clone it, or you can just download the zip as I described over on this file here. I've already got a checkout of it on my LinuxCNC computer, so you can go back to the home directory where I've got that. And here we are. So if I look at the git log for this, we'll see there are two commits. One, the initial commit, where I just copied the old file as is with the bugs. Another one where I fixed those bugs. So we look at the git diff for that. We can see exactly what changes I applied. And there's some white space changes in here by mistake. Whoopsie. And then I changed these parameters to now be pins. That way we can edit them with PyBCP and actually go right to them while the machine's still running. We've got the writing the offset to the current offset. That we're able to read it later on in HAL. And then we've got the thing where we set that last ZN to be 0 instead to be, the last ZN. And that's really all there is to it. Again, you probably do want to make a backup copy of the original thcud.ko just in case you happen to mess up. But once you got these files, you just do the sudo HAL compile install thcud.comp, and then that'll run, install, and you're all ready for the next video. In that one, we'll tie all this shit together and call it a wrap. But until then, peace.